Okay, I think we're good to go. Hello, everyone. Welcome to this meeting on natural language processing, aka NLP. And yeah, so what natural language processing is, it's a bunch of things actually. So some things are like machine translation, so translating from like Chinese to English per se. There's also information retrieval, which is like, think of Google search. When you search on Google, you're actually looking at which website is going to is the most relevant to your Google search. And then there's sentiment analysis. So a lot of people are doing sentiment analysis on like Twitter data, so on tweets and like checking if the tweets are like good or bad, for example, per se, or like movie reviews as well. And then there's information extraction. So let's say you like read in someone's like Facebook profile or something, and you want to extract like some of the interests they have just based off the posts. So like finding topics and stuff. So there's a thing called like topic modeling. And then there's question answering. So this one's like a chatbot. So a lot of sites, like maybe, I don't know anything on top of my head, but like Visa per se, they might have a chatbot that answers like basic answers and questions. And today we'll be actually doing the chatbot and a bit of the information retrieval, which combined will make our chatbot. So that's pretty cool. Let me turn my pointer. So we're going to be doing this thing and this thing as well. Here are some real world applications of NLP. So this is like in Japan, they have this robot that like takes your orders and stuff. And so it has to be able to comprehend what you're ordering. So that's this NLP application. You have Siri trying to understand what you're saying. They use a bunch of language models to predict what you're saying, because some words are they sound the same. So it's hard to choose the right one, but they do it based off probabilities. You have Google, like what do they call this? It's in Gmail, where they would understand what you're trying to say, and just like you can just press tab and it will complete your sentence, which is pretty cool. And then you have Google Translate, of course, that also uses NLP to understand like the meaning of your sentence and how that meaning translates to another language. That's all NLP. So yeah, it's very, very common, and it's a very interesting realm of machine learning. Today, we're going to go over the vector space model and the word vector. Ignore language models. I think it's going to be down here if I have it. And then text pre-processing. This is how we're going to like clean up words. So I'll go over stop words and lemmatization, and then we'll implement the chatbot. So just pretend this was like down here. So I'll start with the vector space model. Actually, does anyone have any questions? Make sure I'm gonna check chat. Okay, I don't think anyone has questions. If you do, just like unmute yourself, please, and just like speak up. Then I don't have to like go back and check. But if not, I'll continue. So we're gonna go over the vector space model, and this is how you represent sentences as a vector. Well, really, you represent documents. So I made the analogy back to Google search, which is how you type in the Google search and it finds the most relevant documents or websites for you based off your search. So it actually was originally built with the vector space model, and I think it's still like somewhat vector space model, but this is how the Google search engine was originally created. It was based off this idea. And actually, whoever, I think the professor who invented it, his like PhD students was the guy who like founded Google search. So this is basically what it is. Let's say you have a corpus. A corpus is pretty much a collection of documents or sentences in our case. And you have a corpus with n unique words. So in all your sentences, you have n unique words. That's going to convert to a coordinate system with n dimensions. So if you had 3 words, 3 unique words, right, then it would just be a 3-dimensional vector space. And if you have a sentence with k unique words, so k is probably less than n. And if you have k unique words, that's going to translate to a vector that has k dimensions greater or equal than 1. Because the vector itself has to have n dimensions, but k of those dimensions will be at least greater than or equal to 1. So that's just the idea right now. And okay, yeah, this is the same thing, just pointing, like showing you it's a translation. And this is what is going to look like illustrated as a graph. So here we're going to have a 3-dimensional space, and each index term is a unique dimension. So think of each term as just a word. And we have this vocabulary of k unique terms, and that will be, I think previously I said it was n unique words, but they have it as k here. So it's a 3-dimensional vector space, and each dimension is a word in our vocabulary. All right, so cat is 1 dimension, dog is another, and lion is 1 more. So if we had another word like elephant, then there would be 4 dimensions. And so when we have a vector in this vector space model, it's really just a sentence. For example, we had this like sentence called cat, cat, cat. Then you would have a value of 3 in the cat dimension, right? So the cat dimension is the first dimension, and this vector has a value of 3 and 0 elsewhere because it does not have dog or lion in it. And so we call this value the weight. Here they call it the term's weight. In this example is just the frequency of that word in that sentence. So D1 is our sentence. It's also called a document because it was made for Google search, like searching documents. Okay, so now let's say we have a new sentence, and instead we had cat, dog, cat, and we have a value, a weight of 2 in the cat dimension, but now we have a weight of 1 in the dog dimension. And we still have a weight of 0 in the lion dimension because there's no lion word in this sentence. And as you may know, the order does not matter. So we could have cat, cat, dog, and it'd still be the same vector shown here, this purple one. You could have dog, cat, cat, and it'll still be the same vector. So you ignore the sequence of the words. And this is called the bag of words model. So this is a very, very basic model. And there's more advanced models that do account for the sequence of the words. And those models are better, but also it requires a lot more computation to go through all these words. Because in real life, there's a lot of words, like millions of words that you have to have in your vocabulary. And so those are millions of dimensions. All right, so here's our final example. And here we have a sentence with all the unique words, right? So here we have a weight of 1 for cat, and a weight of 2 for dog. So 2 in the dog dimension, and 1 lion. So that means the lion dimension also has a weight of 1. So it's in has all 3 words. And again, we ignore the sequence of the words. So that's the vector space model. Is actually pretty simple and is very, very powerful. So this is just a review of what I just went over. And right now, the vector space model, it's an easy measure to, it makes it easy to measure similarity, but it also implies relevance. So we want to see if 2 sentences are similar, we just check their vectors, right? So cat, cat, cat is going to be more similar to cat, cat, dog than cat, cat, cat is similar to dog, 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 right? So the only difference is like this has this has a weight of 2 in the cat dimension, while this has a weight of 3 in the cat dimension. And we can calculate the similarity, and I'll show you that on the next slide. But this is just showing that there's 4 documents or 4 sentences. And here we're going to try to figure out which one is more relevant to the other ones, right? So we need a way to capture this similarity, and there's actually a pretty simple calculation. I'm gonna check chat real quick just to see if there is any questions. Okay, cool. So moving on, we will have this idea of cosine similarity. And this will help us figure out which sentences are more similar to the other. So given two sentences, um, sentence 1 and sentence 2, right? This is just in two-dimensional space, but we can always bring it out to higher dimensional space. We just calculate the angle between these two vectors, right? And so we use cosine similarity, which is going a little bit into the math here. It's just adjacence over hypotenuse, right? So you can calculate that using the weights of the vectors, right, each dimension, and we can calculate the angle. So if two vectors were completely different, then they would have a very large angle between them. But in this case, we have sentence 1 and sentence 2, and they have a very small angle. So that means they're probably more relevant to each other than other vectors, right? And so this is how we can find the relevance between two vectors. Okay, so moving on to how we're going to weight these vectors. So before, we were just taking the number of frequency, the frequency in for each word in that sentence. But we're going to do that. But also, we're going to add this product, not a constant, but it's going to be something we calculate. So before we're doing document dependent, now we're going to do this idea document independent. Okay, so let's take a step back and let's talk about all of the terminology here. So like I said before, we have weights for each word. So each word is weighted. So each dimension is weighted, but we want to recompute the weight. So instead of having the frequency, we're going to have something more. And so a lot of researchers and the common way to do a weighting scheme is to use this thing called TF-IDF, which is term frequency inverse document frequency. So yeah, it's a lot of words, so they shorten it to TF-IDF. So TF is term frequency, and it means the within document term frequency. And then you have IDF, which is inverse document frequency, which is you think about all the documents. So I will show you an image of what that means. So term frequency is looking at a specific document, right? So let's say our document is the document we're querying for. I'm gonna change that back to a sentence. So let's say we type in a sentence to Google search. Our sentence was blah, 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 right? We're gonna look for the frequency of this word in this sentence. But let's say back to our corpus of sentences, right? So our collection of sentences, we can find the frequency of this word in all the documents. But we're not gonna count, I believe we don't count each one. I will get back to you guys on that. But here's the motivation behind term frequency. So the frequency within a document, and I have listed right here, the job is to calculate the number of times the word W occurs in the query document. So this is the query document is pretty much like the sentence you Google search into, like how to code or something. And so what problem does it solve, right? So the problem it solves is how to distinguish the documents which are relevant to the query document D prime. So what this means is remembering back to cosine similarity, if you have two vectors and they're pretty similar, they're going to have this around the same weights, right? Also, maybe they're going to have the same number of word frequencies, right? So that's just, it's a little bit of a similarity. So the solution is to look for documents which have a similar number of occurrences for each word. I hope that makes sense to you guys. So you're pretty much looking for two documents, right? If one document is cat 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 and the other document is cat cat dog, yeah, they're gonna be similar because they have a similar number of occurrences of cat. So that's the example there. Okay, so now we'll talk about inverse document frequency, which is the second part. And this job is the job of this is to calculate the number of documents that contain the word W. And so why do we do this? Well, we want to distinguish between words that are more frequent and provide little value. For example, the, a, we, stuff like that. So these are common words in English vocabulary. So we don't really care about these words. We care about words that are less common and provide more value to the query sentence, right? So the solution is to give smaller weight to words that appear more in more documents, and higher weight to words that appear in less documents. So the word the, I'm pretty sure you'll find that in like most websites. Not all sentences, but a lot of sentences will have the word the. And so in that case, we're going to punish the word the. So we're going to give less weight to the word the. And this is just the whole idea. Finding the number of occurrences, number of documents that contain this word. So it's pretty simple, but like combined, they're very, very powerful. And in the code demonstration, I'll show you guys how to calculate those. And hopefully everything comes together at that point. But now I'm going to talk about text pre-processing. And this is how we filter through data, or not really filter it, but like clean it. We make sure the data is clean so that our algorithms and models can digest the data. So this is just a flowchart of like a common way to pre-process text. So you have like this sentence from like maybe a basketball game, and you have the first step is to tokenize everything. So we break everything into single pieces of words or values. So we have O'Neill, average, 15.2. They're all separate, right? So it's just pretty much breaking everything into smaller pieces. And then we do this thing called text normalization. So here they just did a lowercase. They make everything lowercase, so you don't have to deal with the case sensitivity. Some people also take out punctuation, and yeah, there's a bunch of other text normalization things, but it's just to make the text, you just normalize it so as everything is like smaller. And then we do stopping. So stopping is, I'll show you guys what stopping is, but as you see here, this word and, a very common word, has been removed. So I'll show you in the next slide what stopping actually does. And then there's stemming, which is we want to have a common word. We bring, I guess, like, so for an example, there's words that have pretty much different suffixes, but they're the same common word. A good example is like, I'm just gonna use the example they have. So there's average. So there's a common word, average. And then you have other words like averaged with the D at the end. And then you have averaging, averages with the S. And we just pretty much truncate that. And so pretty much you just want to bring everything to a common word that has, I'm not sure like I don't know how to, what's the correct word for it, or like if there's a better word for this, but I'll show you guys by example. So this is what I mean. So the whole idea is to reduce words to a common base. As you see here, we have organize, organizes, organizing, and the common word is organize. So if you just throw it into a stemming algorithm or a lemmatization algorithm, it will just pretty much take off this and it'll bring it to organize. There's also, you can have like plurals and I don't remember the actual word for this, but You can have apostrophe, right, and like to own possession, to show possession, and you can truncate this and just bring it down to a car. And so the two differences between stemming and lemmatization is stemming actually just chops off the end of the word. So it will chop off the suffix. Sometimes this is good. Sometimes you might have like studies with the IES, and it'll just bring it to stud, which is not like ideal because we know it should be study. So lemmatization actually does a better job at this because it will analyze the word and it'll determine the base word. And this is done through prior research. So people will actually like, okay, we know studies, it shouldn't be truncated to stud. We'll do study instead. So there's a bunch of dictionaries out there. So dictionaries are pretty much like maps from one word to another that already do this for us. And yeah, so it's pretty good in terms of the ecosystem of natural language processing. So I didn't show stopping here, but pretty much you remove any common words. So the and we, these are common words and we remove them. There's a list of stop words out there in the Python libraries. So we can also just look through those lists and check if each word is in that list or not. Okay. So that's actually it for everything we'll do on the chatbot side. I was going to touch a little bit on language model, although it's not relevant to what we'll be going over when we develop the chatbot. So, but I'll just briefly cover it because this is a very big concept in natural language processing, and like a bunch of applications use this idea of language model. And the whole idea is to compute the probability of a sequence of words, or simply a sentence. And so I'm presenting the problem here, and it's what is the probability, let's say we're trying to find the probability of the sentence, the frog jumps high, or in notation, what's the probability of the frog jumps high, right? And we're given this corpus of sentences. So it's just a collection of sentences. And we're going to build a language model to compute this. So we'll be able to compute this based off this. So we have this idea of bag of words and n-grams. And so in the language model, we were actually using a bag of words type model where we don't care about the sequence of the words. So the probability of a word occurring is independent, right? So we don't care if cat came before dog or dog became before cat, right? We just pretty much, it's just a bag of words. We don't even see the order to that sentence. Whereas n-grams actually cares about it. So the probability of word is going to depend on the following n words, right? So let's, for example, high, right? The word high is probably going to depend on jumps, right? You're probably not going to have like the frog is high, or I mean, the frog high or something, right? So high is probably going to depend more on jumps than it is on like the word the or frog, right? So that's the whole idea of n-grams. So we're going to look at the previous n words. So here, the probability of high depends on the past three words, and this is called probably a trigram model. So 3 words before. And we use this idea, I think it was like some theorem or something that allows you to like simplify it to the probability of high given the frog jumps to the probability of high given jumps. And so that allows us to simplify the calculations, right? Because if you have to calculate the past 3 words, it's much easier to calculate just one. And so that's the whole idea of n-grams. So the newer models, like there's this model called GP3. I don't remember the full name, but it's built by OpenAI, I believe, and it's built on billions of parameters. So this model has billions of like weights and stuff, and it calculates based off both directions, right? So it'll look at words before and it'll also look at words after. So for example, a good one like, so let's say we're trying to calculate the probability of the jumps, right? It'll look at the frog. It'll also look at the probability of high. So it'll look both directions, and those are really powerful, and they're really good at finding the probabilities for specific like sentences and stuff. That's just the whole idea. So now I'll jump into the chatbot, but I'm gonna check chat for any questions. Or is there any questions, or was there anything like anyone wanted to share?
I have a question about when you were talking about vectors
Sure.
and talking about the similarities.
Yes.
So in the image you showed, there were two vectors, and it was like the 2D plane, and they have a theta between them.
Yep.
So if there were more dimensions, would you be taking into account multiple um angles to measure the similarity?
Yes. So you would need to have a way to figure out. So you have, let's say you have three dimensions, right? So you have two angles between them, um, and it'd be a plane. And so if you were going to figure out which one is more relevant to the other, you can just, one thing you can do is you can add all the angles together, and that's one way to check as well. Um, if you wanted to, if you cared about like certain specific dimensions more than others, you can just worry about those dimensions. And so those are just two ideas. Um, I'm not sure like how everyone, like what's the common way to go about this, but this would be the idea.
Yeah, okay.
You would just check all angles, and you could simply like add them all together or
Yeah,
something.
that makes sense.
There's
Thank
there's
you.
yeah, there's a bunch of ways you can do it. Um, I did miss one slide. So let me explain the whole process of what we'll do in the code. So if we're going to build our chatbot, we need to first get a corpus of documents. In our case, questions, right? So our chatbot is going to answer questions. Um, and so I have a list, a text file provided, but one way you can do this is like web scraping or stuff like that. And then you need to map each question to a list of possible responses. So you need to have answers for them. And then we need to pre-process our text using some of the methods I showed before. So like text normalization, stopping, stuff like that. And then we're going to create our vector space model. So there's libraries that provide the vector space model creation. And then we're just going to find the most relevant question using the cosine similarity. And then we'll return the question that is most relevant to or most similar to our user's question. So I'll show you that in here. So open up the notebook, and then I'll create a separate one to code it from scratch. But I just want to quickly show you guys this part. Um, so you have term frequency and inverse document frequency. And this is, you take the product of that, and that's how we're going to weight a single dimension. And so the frequency is calculated by the number of times the word W appears in our document divided by the total number of words in the document, right? And then you have inverse document frequency. And just as a reminder, we just want to give a lower score to common words and a higher score to uncommon words. I mean, it's not going to be the most, it's not like going to fix all cases, but it helps. It definitely helps a lot. So, and we calculate this by taking a ratio. So the total number of documents, so n, let's say you had n documents, divided by the number of documents that have the word W, and then take the log of that. So if you take the log of that, if you have a fraction that's like small, it's going to be even smaller, I believe. But we also have the how we're going to calculate cosine similarity. So Jonathan, I think you mentioned like calculating multiple dimensions. I don't know the exact formula, but this is how you do it in 2 dimensions. So I'm sure they have like some formula to calculate given, well, you just take a dot product here. So if you take a dot product, then it wouldn't matter how many dimensions I guess there is. So maybe the cosine is just a scalar value, even in like a high dimensional vector. So I guess it is like a single value. But we have this vector space, right? And this is what our corpus of questions are going to be put into. So I hope that makes sense. And then we also have a query, right? So if when our user asks a question, we also vectorize it. We need to create a vector for that question, so we can find which chatbot question is the most similar to our user's question. So that's it. I'll code it up. There's a good amount of code, so yeah, let's get into it. If there's any questions as I code, please feel free to speak up. So we're going to use Google Colab here. And for those who are unfamiliar with Google Colab, it's pretty much an IPython notebook. So what IPython notebook is, it allows you to write Python code in blocks. And you can save these blocks. So you can keep running these blocks. You don't have to run the entire Python script over and over. Okay, so let's get started. First thing is we're going to get the data. So our data is actually here in the chatbot corpus. As you see here, we have a bunch of questions. So question and then followed by the answer. Yeah, there's a bunch of questions. I don't remember how I came upon this, but yeah, they have a bunch of interesting questions and they're all like about bots and stuff. So it's pretty cool. So we're gonna get the raw text from this so we can use it. So if you click raw, you can get the raw text. And then, yeah, let's get started. So I'm importing requests, which allows us to send a request to a server, and then we can just get all the data. So corpus equals request.get URL. So we have that. And then let's take a look at this. So you can see here, it is just the text that I showed you guys earlier. So let me add the dot text part. Okay. So now we're gonna do a little bit like data processing, not like pre-processing anything, but we need to make sure we strip out any like white space, and we also want to split the text based off a new line. So now our data can be put into an array. So we can get the very first question like this, or we can get the question and answer like so. So how's it going? Good. So that's our question and answer. And so now we're going to need to build a dictionary. So each question is going to map to a list of responses. And so we'll have question to response as our dictionary. And then we'll also have a list of questions that we can eventually save. So I guess you can also do like questions keys, but I'm just going to add it into a list. Okay, so now we're going to do a for loop, and it's pretty much going to grab the question and the answer, which is every 2 rows, we're going to grab the first row and the second row. That's it. Okay, so now we need to create a list for each question, right? So if we don't have, if we already added a list, then we'll just append this response to the list. So this is what that's doing here. So pretty much this is getting it's checking if questions are ready in the dictionary. If it is, get the list of responses. And now we're just going to append the response we have here to that list. If not, it will just give us an empty list, and we'll still append, and that's fine. And then we're going to add this to our list of questions that we'll eventually use to cover everything. Okay. So now let's look at this dictionary. Question to response. And so now everything is a dictionary, right? So this question, how's it going, is going to have multiple responses, and we'll just have that as a list. That's how it looks like. Okay, so now we're going to do some of the logic for the pre-processing. So there's this library called NLTK, which is the Natural Language Toolkit, and it has like these stop words that I talked about. It also has ways to tokenize everything and normalize stuff using like punctuation, or you put everything in lowercase. And then you're also going to use something from the string library. Okay, so first thing we're going to do is going to download the punctuation. Whoops, the punctuation set. So it's going to just have a list of like punctuations that we'll eventually remove. And then we have WordNet, which is how we're going to convert everything to a base word using the lemmatization. So someone has a dictionary that converts a word to its base word, and we're just going to use it. All right, so we're going to build a lemmatizer. And it's just an object that we'll create. And then we're also going to create a table. And this table is going to have, let's see, is going to have all the punctuation. And we're going to convert those punctuation to emptiness. Not emptiness, to nothing. So this is pretty much just creating a dictionary. Just making sure that my things are in order here. Okay, and then we're going to do this for each punctuation in the punctuation string dot punctuation. Okay. Okay. I think that should work. If I look into this, it should be a table. Okay. Okay. I don't know what that means. I'm just gonna copy and paste it from the thing. Make sure I don't mess up anything. Okay, I guess it was right. But anyways, I'll probably just like briefly or just copy over the non-important parts. The more important part is this this formula we're going to write out, or this function we're going to write out. And this will do the tokenization and also do the normalization and the lemmatization. So it's a lot. So it's a three-step process, right? So first thing we need to do is we need to normalize it. And we pretty much do a text.lower. And then we also remove any of the punctuation we find. So all the punctuation is gone. And then we're going to tokenize it. So break it into smaller pieces. And that will be in there, tokenize. So this is in the natural language toolkit, which actually does this for you. And it'll take in this function, normalize text. It will do this on the normalized text, not the function. And then we're going to lemmatize everything. And this is also using the NLTK, where we're going to lemmatize each token, tokens for token and tokens. So just give me 1 second to check everything. Lemmatizer. So the lemmatizer has a lemmatize function, and we're just going to lemmatize everything. And then we're going to return it. So yeah, that's how we're going to pre-process everything. Okay, so this code is not too important, so I'm just going to copy it over. But what it does is we're just gonna, if you remember, we have a list of responses. It's just gonna choose a random one. So this is just like gonna make the quality of the chatbot better. Okay, so now let's actually build the vector space model. So we're gonna use this library called sklearn. So sklearn is a machine learning library that has a bunch of APIs. So we're just going to use, I'm going to copy it. I don't want to type everything and then I can explain it. Okay, so we have feature extraction, which is going to have the term frequency inverse document frequency vectorizer. So this is going to it has the algorithm to calculate these two frequencies, and then it's just going to vectorize a sentence. That's all it does. And then we also have something to calculate the cosine similarity between two vectors. So that's going to be very helpful for us. And this is going to be this is going to be the thing that creates a vector space model for us. So we're going to create a respond function. All right. So let's just say we have, we implemented this. I'm going to show you guys how we're going to build the vector space now. So we have the VSM, and I think I put TF space here. And we're just going to create a object for that. And we're going to give it the tokenizer that we wrote up here. And so you just pass in that function. And so that will take care of everything for us too. So yeah, that's it. So this is a vector space. And now we will implement the response question. Okay, so we're gonna have this question list, right? So this is pretty much our corpus of documents. And what we're gonna do is we're gonna convert each of the sentence or question in the question list, right, to a vector. But we want to also do the same thing for user questions, right? So we're gonna throw the user question in there. So it also gets vectorized when we end up doing that. And so we compute a vector for each question and the user question. And so it'll be a matrix, right? So we have the vector space model we created up here, and we're going to fit it. So it's going to go ahead and create that vector space for us, given the list of questions. So that's what it does. And now we need to calculate the user question vector, right? So we already have it calculated. We just need to go ahead and get it from the matrix. So I get -1 because it'll be the last vector in there. Okay, so let's go ahead and compute the similarity score between all the vectors, I believe. So you're going to use the cosine similarity here, and it takes in two things. First, takes in the vector of our user's question, and then we also going to pass a list of vectors for the remaining questions. So TF IDF matrix, and then we're just going to get all of them except the last one, right? So the last one was a user's question. So that's a similarity score. And now we just need to get the highest similarity. And
So the
that
negative
one we
one
can use
automatically goes to the
called
end of it.
argmax. So similarity score dot argmax, right? So we're going to find which index has the largest cosine similarity, or actually you want the smallest one, right? So why did we get the argmax here? I believe is this score will give it a higher value if you have a smaller cosine angle. So that's why we get the higher similarity score. Okay, so now we get the vector for this one. So we get the vector, and then we have the score. Okay, so now we're going to do a little bit of the logic for the chatbot. So you just do, if there was no vector that best was relevant to our vector, then we'll do nothing. In most cases, that won't happen, right? Because there probably is some vector that will have a good angle, or sorry, a smaller angle, so it's more similar. But just in case, we'll just have some logic there. Be like, I don't understand. Else, we have the question, right? So whatever question is here, we're going to use it. So robo response equals select random response based off our question. So question list, and we get the index here. Okay, so that's it. Now we're just going to get the user question from the user's input. I'll go ahead to normalize it anyways. And then we're going to remove the punctuation too. I believe you don't need this part actually. And yeah, actually, like let's just run it now. So let's ask a question. What is one of the questions up here? Okay, so let's see how is it going first. How is it going? Just to see if our chatbot is working. We need to print this. Sorry. Run this again. How is it going? Okay, that's definitely not working. Let's see. Did I? Oh, return robo response, but I don't think that's the issue here. All right, I'm not going to do too much of debugging. I hope like that walkthrough was helpful. But let's just see if this. Okay, I already know what I did wrong. I'm just going to print this. So I forgot to call the function. All right, so let's see. How's it going? Respond is not define. Respond.
I think you need to call it self.response.
Okay. So yeah, I'm not gonna go debug that because I have the code here. So I'm just gonna run this all, and I'll show you guys what what it ends up working as. And so we can test out like a couple questions, and then yeah. So we'll go ahead and end of line. Okay, so how is it going? So it'll do all the calculations and it'll find the random question. So I remember like it was trying to get a random one. Okay, so that's fine. So we changed it up a little bit. So we said like how is it going? It should still give us that question, right? Because we normalized it. Let's say what's another like valid question that we can do? How I'm going to look at some questions here. Okay, tell me a joke. Please, let's say we had, please tell me a funny joke. So it like just somehow knows this vector is similar to tell me a joke. And it can do that by just looking at comparing the cosine similarities. So yeah, that's just the power of the chatbot. I don't want to like put it out, like have this meeting too long, but I hope everyone like learned a bit about the NLTK and sklearn here. And yeah, it doesn't really take too much code to implement everything, because there's a bunch of libraries out there. Yeah, thank you guys. Is there any questions on anything I did? Okay, there's no questions, so that's good. I just want to talk a little bit about the last meeting, or it won't be the very last meeting, but it'll be the last meeting about machine learning concepts. So in 2 weeks, we'll have another meeting on Monday, and it'll be about ensemble learning. So this is a glimpse of ensemble learning. You pretty much combine a bunch of models together, and you have a single model based off that bunch of models, right? So here you have a bunch of models, and we want to make a prediction um, based off what they say, the group of models. So I will go over that in 2 weeks, and we'll code something up, of course. And yeah, and then after Thanksgiving break, I will have one last meeting on. It will be about just stuff on machine learning, like careers in machine learning, research, classes to take, and like I guess state of the art stuff. We can check that out. Or it's also a time for you guys to ask any questions and talk to other people as well. So yeah, thank you guys for coming. If I will also stick around for any if there's anyone who has questions. But if that's it, thank you.